Welcome to this presentation on maths and medicine. Which comes first? I'm John Aston. I'm the Harding Professor for Statistics in Public Life, and I'm also a co-director of the Centre for Maths of Information in Healthcare. And I'm really also pleased to introduce Carola, my other co-director.
Yeah, it's my pleasure to be here today together with John. I'm Carola Schönlieb. I'm Professor of Applied Mathematics in Cambridge. So we really look forward to having a very, hopefully, interesting, fruitful discussion with all of you. But before that, John and I met last week, and we had a good conversation about mathematics and medicine. This is what we're going to show you first. We recorded a video for you, and after that, there will be a Q&A session where we will be very happy to receive lots of questions from you. So I guess without further ado, let's start the video. Hello, John. Nice to see you.
And it's good to see you too, Carola.
Really a pleasure talking to our alumni today about mathematics and medicine.
Exactly. And which came first?
Exactly. So talking about which came first, I mean, we have known each other now for more than 5 years, but I think I never asked you what came first for you. How did you get into mathematics from medicine?
Well, so for me, maths and medicine have always been together, although I think probably maths came first from school. But I think maths really took a different dimension for me when I actually saw that it could be used in practical settings. So I was really lucky. When I was 16, I got a summer job working in a hospital. And they actually let me have access to some data and to play with it. So I got to look at some very in school. I got to play with some data and actually fit some very simple models through the data. Now, when I was looking at them, they didn't look simple to me. I was 16, I was very naive, I didn't know what these things were, but they let me have a go at this. This was cancer data, and I was really lucky that I got to sort of process this cancer data and look to see what was happening in the trend in the cancer data. That was a 1-week sort of summer internship kind of idea when I was at school. That turned into, well, why don't you come back to next week and finish off the project, which was really great. So I got to do that. And that turned into a summer job the next year. So I did that, and that sort of suddenly allowed me to see that I could actually use maths to solve problems that were not actually mathematical.
Was that, you think, very important for you to go for studying mathematics at university?
I think so. I think at that point in time, I couldn't decide whether I wanted to do maths or physics. And I think being able to see that I could actually do maths and understand some problems in healthcare was a really interesting way of exploring that maths was going to be relevant just beyond the things we were doing at school. For me, that then sort of carried on. I came to Cambridge, did my undergrad here, and during the summers I continued to work on medical imaging data. I was really lucky. I got to go to Montreal to present some of the results that I'd been working on. And at that point, I suddenly started to see that there were some really interesting connections between data and medicine, putting those together, building mathematical models that could actually really help explain what was going on, and then take that forward in order to understand what was really going on in the medical applications. So, picture on the screen now you'll see is a 3-dimensional picture of the brain. This is actually coming from an experiment where they did some studies about the perception of pain. So you'll see that the area of the brain outlined, but you also see the areas that correspond to pain. But for me, in actual fact, you also see that it's just a 3-dimensional box underneath this underlying picture. From that, I can actually abstract the problem to a 3-dimensional mathematical problem. And from that, you can build some notions of geometry, take the statistics that we knew about, how to extend that into multiple dimensions, and use that to understand how to analyze that brain image and come up with those particular regions that were associated with pain. So for me, the ability to be able to see that you've got an image of a brain, yet the things that are coming out of that are all mathematically generated.
You can abstract them.
Is really powerful. And I think it was also the first time that I really got to see when working on that project that I could take something that I knew from maths, apply it in an area that other people hadn't yet had to go applying it for, and come up with a result that other people didn't see back in the medical space.
So mathematics really opened up a new perspective onto this problem.
Exactly. Yeah. And for that made me really excited because, to be honest, I love the maths. I love spending time doing the maths. But to know that it actually helped somebody else out, understand something else, was a really, really satisfying thing.
Yeah, super interesting. Yeah, I can see that this is really encouraging.
So what about you? Which came first, maths or medicine?
So for me, also definitely mathematics came first, like in your case, but much later than for you starting in school. I was really encountering mathematics and the variety of its applications when starting PhD research. And my research for a PhD was in the area of nonlinear partial differential equations. So these are equations that describe various phenomena in nature through quantifying variations of functions and their relationship to each other through looking at derivatives of these functions and putting them into context to each other. And I mean, these partial differential equations have applications in all kinds of areas of life and science and in biology, in economics and social sciences, and in healthcare.
So really do have applications across the board.
Definitely. And I was actually the first thing that fascinated me about application-wise about these was that at the time when I was looking at this Cahn-Hilliard equation, there was a group at UCLA developing a certain instance of this equation for virtual image restoration, what is called also image inpainting. So this is the task when you have an image, like an image that you take with your mobile phone or something like this, and you have gaps in this image, corruptions, because maybe you have an occlusion, or that could also be seen as a corruption. You have an occlusion of someone walking into what you actually wanted to take a picture of, or you could even think of an obstruction of something that you have some blur somewhere, and actually you want to have a sharp image of this place. So this can be formulated as an interpolation task, where you say you look at the content of the image that you took, that you're happy with, and you say that the rest of this image, the gaps you have, the damages or the occlusions, you want to replace by something that is suggested by the surrounding content. And you can use PDEs to do this interpolation, to propagate the colors and the structures, edges and so on into the whole. And you see actually an example of this now on the screen of a pufferfish, where we put in some scribbles, and these scribbles are removed via this PDE.
So not unlike what people do in art history and in museums, and when they clean up images and make them look beautiful.
Yes, indeed. And actually, this application of art restoration came even for me first to looking at medicine. And so the first application really interdisciplinary work that I did was with art historians and art conservators, to help them by showing them virtually how different restorations could look like, to actually do their restoration, which is the restoration on the Neidhardt frescoes in Vienna.
But you did that with maths?
So I did that with math, exactly. And that, from that time on, I would say my approach to mathematics also changed, because from that time on, this question about which came first, mathematics or medicine, turned around, and the application came first. And then I also I started working with clinicians, in particular with radiologists, looking at making their images better. So again, thinking about this problem, abstracting this as a virtual image restoration problem, of getting the most out of images. And the interesting thing about medical images also is that they are, most of them, images that clinicians, radiologists are looking at, are not acquired by the machine as an image directly. But these are so-called tomographic measurements that you take, like computed tomography, magnetic resonance tomography, positron emission tomography, which is what you're seeing now on the screen, where we have really shown that you can go beyond what is implemented on the scanners themselves with techniques that are linked to partial differential equations and things like total variation regularization and so on. So this is definitely.
And that's
really
because you
fascinating.
can't take a picture of the inside of your body. You
Exactly.
need something else to be able to reconstruct.
Like X-rays, exactly. Yeah.
And you use maths to help that reconstruction.
Yes, so that is exactly. So the mathematics are both for going all the way from these measurements to an image, and sort of describing this physical process, as well as in doing this this transformation from the measurements to an image in the best possible way. There is a lot of degree of freedom of different images describing the same measurements, and so we want to find the best one that can help the clinician to see more, to see things earlier, even if they're very small. We want to enhance them so the radiologist can look at them.
And that motivates the maths that you want to do.
It does, and I think although still similar to what you said, the mathematics itself, I mean, these are really very challenging mathematical objects. These nonlinear PDEs and total variation regularization are non-smooth, very non-smooth optimization problems. They're mathematically really challenging, touch upon several areas in mathematics. But then plus, you get this additional satisfaction from not just solving an interesting math problem, but also making a difference. So yeah, that's definitely really, really nice.
No, I think this interplay between different areas of mathematics is something that's really exciting. And I think the fact that we can do that in terms of medicine just gives it an added extra. But for me, one of the really great advantages is the fact that I get to look at other areas of maths as well, the one I particularly work on.
Yeah, I totally agree. I mean, just take as an example image denoising. I mean, to solve image denoising with an algorithm, various areas of mathematics need to play their part. I mean, image denoising really is about decomposing an image into the actual clean image, the content of the image, and the noise that you want to get rid of. And in order to do this, you need to characterize both. Now, noise is random, right?
And for me, that's the bit that I find interesting. As a statistician, I spend a lot of time worrying about randomness and how I can characterize that, how I can model that, how I can capture the things in there that are structured, and how I can then try to characterize the bits that are unstructured so that you can then build algorithms that take that into account when you fit those algorithms to them. Is the noise a particular distribution? Does it have a particular pattern to it? And can I then extract that from different ways of putting the models together so that I get the model and the noise together? But then those models can be really mathematical, and that's where things that you do come in.
Exactly. And I mean, then once you've characterized the noise, which is what you said, statistics, probability, then we also on the other side need to characterize what is left, what is the image content in order to make this really, really good. And so image content, if you're just looking at the video that is being shot from us now, what does it consist of? It consists of larger scale objects, geometric objects, tables, chairs, our silhouettes, the blackboard, as well as finer grained structures, such as repetitive patterns, texture, like the texture of our hair or the carpet and things like that. And then on top of this, the color. So this characterizing this in terms of a mathematical equation, really again boils down to areas like geometry, harmonic analysis, partial differential equations, and so on and so forth. So this is really, really, I think, it really shows the interplay. And then even when you go further, once we have this mathematical model, which is now fed by statistics, by ideas from probability, concepts from geometry, then you need to solve this mathematical model on a computer. And this often boils down to a really challenging, very large scale, non-smooth optimization problem, which then you need ideas from numerical analysis, from optimization, and so on. So,
and I think that that's part of what's really exciting, is that I can add my expertise, but I also learn an awful lot. And I mean, one of the great things about the centre that we have, the Centre for Maths and Information in Healthcare, is that we can bring together different expertise across mathematics to solve big problems in healthcare. And I think the fact that we work with people who really do know about geometry, people who really do know about numerical analysis, people who really do know, like yourself, about PDEs, statisticians, probabilists, bringing all these things together, really starting now to think about things in machine learning, which we can take a mathematical viewpoint from as well, bringing all those together to really solve real-world direct problems actually provides a focus to these things which you often don't get otherwise. I think if you really have a problem you are trying to solve, you can't take shortcuts. You can't say, oh, well, that's a bit too difficult, I'm going to ignore that. No, you need to have an image out at the end that works. You need to have something that a clinician can look at and say, yeah, that's actually better than what I had before.
Yeah.
And from that point of view, it makes you drive really good, really deep mathematics. And for that makes me really exciting. And I think the statistics that we do from that, is some of the best statistics I've done from just out of statistics, but it has a real application too.
Exactly, and this is also exciting because it can take various forms, right? So you start with a medical problem, you derive a mathematical model for this, and then there are different directions you can go, right? Either the medicine keeps taking over and you use mathematics to help to solve the medical problem, but then also the mathematical problem can take over in the sense that we find out, wow, this is so interesting, there are so many open questions about this mathematical model that we can ask and that we can understand better, and then also having more understanding of this mathematical modeling can again feed back to saying more confidently what we understand through this mathematical model for the medical question.
Exactly. So for example, one of the things that I'm working on at the moment is working out how we might combine some of the ideas of using PDEs on surfaces. So imagine that you've got the brain and the fact that, as you saw in the picture earlier, and I'll show you another picture now of what the brain looks like. It's a surface, it's not smooth, it's not a ball. Your brain has structure to it, and in particular the brain has folds in it. And so if I want to look at the distance between this point here and this point here, I need to know whether I can join them in a straight line together, whether I have to go down a fold and come back up again. Now, in order to be able to actually make use of the data, I have to know where those folds are. And more importantly, when I look at my statistical analysis and I say, this point and this point, how are they related? I need to know that you need to go down the fold in order to relate them. And so for that, I need to build models that have PDEs involved. I need to have models that have statistics involved. I need to understand how I'm getting data from populations. That's something that statistics is very good at, trying to bring population level data together. And then I need to understand how I can actually solve that on a computer. And I can use numerical methods in order to really solve that, to solve the statistical problem I want to know of. What does this population look like? What is the variation in this population? How is your brain different from my brain? How is my connections in my brain different from the connections in your brain? And how do they vary across a population? So that when you have a new person come into the clinic, you can understand, they lie in a normal range, or no, there's something quite different happening, which gives clinicians an idea of what the idea of normality is. What does a normal person look like, and how much range of variation is there, as opposed to a set of patients who may well have very different structures in their brain, and you want to be able to characterize those from the images that you see.
Yeah, and I think this is a perfect example of where actually, two very different mathematicians like the two of us
Exactly.
Are needed to work together to solve these type of problems. And this is indeed actually a related problem. I think, John, is the problem that we started on collaborating with
Exactly.
each other. So it's very nice that you bring this up. I mean, if I'm thinking about a current project that we are working on together with neurosurgeons here in Cambridge, the main driver of this project is actually a neurosurgeon. A research question that he was asking, which is, can we use MRIs of glioblastoma patients? Glioblastoma is a very, very aggressive tumor in the brain. Can we use MRI data of glioblastoma patients to predict survival rates of these patients, to predict once they have undergone surgery whether the tumor is coming back, how quickly it's coming back, where it's coming back, and things like this. And through seeing the potential in the data, he understood that he needs mathematics in order to actually develop a model that can systematically extract this data from this information from this MRI data and help him build such prediction models. And this is how we got in touch, and this is how he actually moved more and more and got more and more confident also with mathematics.
And I think that's one of the things that's really exciting, is that it's not just us saying maths is great. It's actually the clinicians realising that in actually by working together, we can all solve problems. That, you know, there are some really interesting mathematical problems that we are going to have to spend some time really working through, but that they can come to us with those problems and suggest interesting things and see how the whole collaboration together can actually generate better results. And for me, that's something that's been really interesting to see, just how much recognition is that each has to help in their own part in order for it to actually solve the whole problem itself.
Yeah.
So the Centre for Maths of Information in Healthcare, it's obviously had a huge impact in terms of bringing people together, but what's next? What does the future hold from your point of view in terms of where it might go?
I mean, what we have seen in the last couple of years was really a revolution in terms of data analytics for healthcare through the evolution of deep neural networks, machine learning, and the really super impressive performance that we have seen from these neural networks on, classifying cats and dogs against each other, but also in some instances for solving problems in healthcare, answering some open questions. So that is definitely something that we need to study more, we need to understand better, because although there are these really impressive performances that we can see, that neural networks can do cancer grading better than some radiologists, for instance, if they're trained on really, really high quality data. The problem with this is, if we're just happy with this, we can't really, first of all, systematically change these models because we don't understand how they work. Why is it actually that they can do these tasks so well? So understanding them is crucial for changing them, for systematically changing them, for also understanding the limitations, because as much as we have heard all these super success stories of deep neural networks, we have also seen really failure cases that are extremely frightening, especially when thinking about a sensitive application areas such as medicine and healthcare. Adversarial examples, for instance, you perturb your input to a network only a little bit and all of a sudden you get a totally different answer. And so these things can't be in a healthcare medical context. So we need to understand how these networks work, how we can constrain them to make them work more reliably, that we can also attach to predictions of these networks some error bars, some confidence measures. So things like this are really important, and I think this will definitely be an exciting way forward in mathematics for healthcare.
But when people think about deep learning, neural networks, they think of computer science, they think of engineering. What's the role of maths? What's the role of statistics? What do you think? Why is it a healthcare and maths question, not a computer science question?
I mean, actually, machine learning, if you think about it, is mathematics, is statistics. It's full of it, right? I mean, even when you are trying to formalize how a neural network takes the input and produces an output, this is a concatenation of a bunch of linear and nonlinear functions that are put together and that have lots of free parameters. That's the power of it, that you train them to fit the data. But this is a mathematical object, right? The training of these networks, the optimization of these parameters is a mathematical problem. It's an optimization problem. It's a constrained optimization problem. It's an optimal control problem. That is a proper area in mathematics with lots of ideas that are feeding now back into deep learning and developing algorithms for the training. When you think about this question, why, if you train a neural network on a data set, on a training set, why does it go beyond this training set? Why can it actually also predict kind of the correct things for new data that is coming in this outside of this training set. This is goes towards statistics, isn't it?
I mean, you wouldn't expect me to say anything other than yes, in the sense that for me, there is such an interplay between statistics, machine learning and maths that it's sort of impossible to separate them out. I think for me, really trying to understand what the generalization properties are, as we were talking about earlier, statistics is concerned with populations, and in reality, what you want to do with a machine learning model or a deep learning model is take some training data and generalize that to a much bigger set of data or a population. And I think trying to work out how to deal with deep learning in that form really does give you a way to enter it in using some of the classical statistical methods. We've had, statistics has been around for 100 years. And using some of the techniques that were designed a long time ago, but doing them in a modern way, thinking about them in a modern context, really trying to bring them together, not saying, oh, there's nothing to learn over here, but really trying to embrace bringing together the ideas of really clever ideas that have come from machine learning and understand how to put them together with the ideas from statistics in terms of design, in terms of estimation, in terms of inference, really helps you kind of understand what those predictions mean. And I think the other thing that's really key about maths is that maths is concerned with proof. Maths is really concerned about understanding what's going on and proving it does something or does not do something. And I think that while we're really excited about what happens in machine learning, we'd really like to prove that it's going to do something. We'd really like to understand when it works and when it doesn't work.
Exactly.
And I think having a mathematical framework behind that allows you to get that idea of when is it going to work and when is it not going to work. And at least have some ideas about the kind of situations where it's most likely to do the right thing, or where sometimes, in actual fact, as you said, small changes could lead to big changes in the answer that comes out. And I think maths has an awful lot to add to that, both from a statistics point of view, but also the rest of maths as well, where it comes in from that idea of understanding how to prove things work.
And this is actually yet another good example of where different areas of mathematics are playing together to answer really some of the big open questions in deep learning, like generalizability, expressivity, the learning capabilities, and so on, as well as medicine kind of also coming first in the sense that we also want this reliability, and also reliability in terms of being really certain by proving something and knowing when these things work, under which conditions and so on, because we are looking at a very sensitive applications. We want that these models, if they are at some point complementing clinicians, radiologists, or maybe in some cases even taking some of the work away from them, we want we want to understand what the error margins are.
Exactly.
So in a way, medicine is in this case coming first again.
Absolutely. I think it really is driving the kind of maths that needs to be done to really understand what is the rates that these things work, what is their reliability. These are all questions that statistics and maths can answer. And I think pulling that together with the driving force of the fact that we really want to know how this works in a cardiovascular example or in an oncology example, where people will be using it for either computer-aided decision-making or, as you said, in certain cases, to triage so that people don't have to spend their time on what would be perceived to be easy questions to classify. What we would need to make sure is that they really are easy from the computer's point of view.
And I think this is also, this philosophy also definitely changed how we do mathematics here in Cambridge. If you think about the Mathematics of Information PhD training program, we're really educating our early career researchers in exactly appreciating this interplay and looking at important problems. If you think about the Mathematics of Deep Learning program that is also starting here in Cambridge now, these are all really important questions that is really also a privilege to be here and work together with our brilliant colleagues who are very open and curious about questions behind these mathematical objects.
Yeah, I mean, I couldn't agree more. I mean, I feel so privileged to be here where I have world-class mathematicians to work with, yourself included, and really gain their expertise and use that in my research. But then also have world-class people in many, many different areas, not least healthcare, clinical medicine, really who can actually, from a research point of view, really ask those interesting questions and also are interested enough to spend time to work out what I do and then really work together to come up with interesting questions and also interesting answers. And I think the fact that you can bring all these people together in Cambridge puts us in an incredibly privileged position. And I think that the work I've done has benefited immensely from being here.
Yeah, the same for me. I think this openness of researchers here, this genuine curiosity for answering questions, interesting problems, is what I think is the basis for the success of the things that we are doing here. And definitely also the passion that people bring to the table.
So I don't know about you, but from my point of view, I don't think I can now tell which comes first. I think for me, when I ask interesting questions in maths, they often have direct applications in healthcare. And when I hear about interesting questions in healthcare, my first thing is to think about how can I turn that into a maths problem. And I think for me, that really helps me feel like I can put them together and work with great people to solve problems which I hope really have impact far outside just maths.
Yeah, so I think this interplay definitely is fruitful. And I'm looking forward to continuing doing research together with you, John.
Absolutely. I think the future looks really positive.
Yeah, I agree.
Well, we hope you enjoyed the video just as much as we enjoyed making it, but we really would like to get your questions so that we can have a discussion about maths in healthcare, and in particular how we can use maths to inform healthcare and healthcare to inform mathematics questions. And we're really lucky we've already got some questions, and I think the first one I'm going to choose is really sort of follows on directly from the video, and how sort of deep learning and machine learning is sort of coming to the prominence in maths and healthcare. And I think, Carola, this is probably one for you. So, Carola, what's your view of the scope for artificial intelligence, AI, in solving the problems such as protein folding, which has been done by sort of Google's DeepMind, and moving that beyond that into other medical problems?
Yeah, super interesting question. Thank you very much. So what the question is about is Google DeepMind's AlphaFold that definitely has resulted in a lot of excitement in the scientific community, in particular for structural biologists. And it definitely shows the potential for what deep learning can do to really help us drive science forward. I mean, there are, in the community, there are these conversations going on that the AlphaFold team could, in fact, be a possible candidate for the next Nobel Prize, even. Yeah? Because really, what that means is, since you can now, I mean, if you believe in all of that, and if you look at the capabilities of AlphaFold, then the protein folding problem is solved. So now structural biologists can really focus on how our body basically works. And I think this is super exciting. So this is one. Now, how do we take this concept to other medical problems? So one of the things with protein folding is, and also in that Google DeepMind has been working on that, is that you have a lot of data to train on. You have very good simulators for protein folding, and Google DeepMind has huge computational hardware, also facilities to train these huge models. Now, in a medical context, you can definitely see where this can go as well. What we need in order to do this step is, first of all, have enough data. And this is something that requires collaboration across hospitals, across universities, across countries to bring all of this together. Data harmonization. The data that is produced in hospitals is unfortunately usually quite messy and heterogeneous. So you can't just put this all together and then put this into your model. And then, of course, if you take this into a sensitive area, such as we have also discussed in the video, such as medicine, healthcare, you really want to understand how these models work, and we still don't understand that. So there is definitely, you can see a lot of potential, for really getting this into medical use, there's lots of things on the collaboration side, data sharing side, on the math side, and then also, of course, on the regulatory, I can never pronounce this word, side. Yeah? So there are things to do, but it's super exciting times. So maybe following up a little bit on that, I'm going to ask you, John, the next question coming from our audience. So John, can you give an example of how the mathematical investigation resulted in the medics seeing something they couldn't previously see?
You know, I mean, I think that's a really good question, because what we really want to do with all this maths is to actually be able to allow doctors and others to see and understand things that they haven't been able to understand previously. So Carola in the video showed some pictures of positron emission tomography, PET imaging. And so I was fortunate enough to work on a number of PET imaging projects where the idea of PET imaging is that it allows you to measure, in the case of the work we were doing, chemical levels in the brain. Now, you can't do that by actually measuring chemical levels in the brain, because, of course, that would be far too invasive. And yet you still want to understand what those chemical levels do and how that might be responsible for certain things. So in particular, the studies I was involved in were very interested in addiction and looking at different addictive substances, so drugs, nicotine, even video games. And they were really interested in how the levels of chemicals changed in the body when you were doing these activities. Now, you can't put enough radioactivity into someone in order to do that, just measure it directly. You need to have mathematical models to make it safe in order to understand those things. So by putting together the mathematical models, and in particular, really taking the information that you could have from multiple subjects, and by combining multiple subjects together, which is intrinsically a mathematical problem. How do I take data from one person and add it to data from another? It's a statistical problem. I need to understand the uncertainty, the differences between individuals, and really understand what happens and how those differences relate to the difference in tasks. So whether someone was doing, someone who had spent a lot of time smoking had just smoked, or someone who had been smoking was off cigarettes for a while, look at the levels of chemical to do with addiction. And being able to look at those, the mathematical models that we produced enable people to say, not only there is a difference in brain chemical level between this condition and that condition, smoking and not smoking, but also to actually quantify it and say, well, the levels of difference is this much with this much uncertainty on it. And that's allowed people to understand the nature of addiction between illegal drugs and addiction with smoking, the nature of addiction with video games, and really understand what kind of changes the brain was going through when those activities were happening. So for me, it allowed a completely new understanding of what was happening to the brain during addiction, which then allows people to sort of make new ideas about how you might treat these when you have very strong addiction, how you might treat these things, because they know the kind of levels of brain chemical changes that are involved and what you then might be able to do in order to take treatment to the next step by affecting those brain chemical changes. So for me, that was something where they would not have been able to understand the problem at all without the maths. But once they had the maths, they could take it in many, many different directions.
Thank you. Thank you, John.
So another question for Carola. How could the models that you develop go beyond just the sort of direct medical application, but actually into the whole of healthcare itself, so maybe the operations of hospitals, healthcare settings? Could those similar models be used in those ways?
Yeah, definitely. And I think actually this is what we are really working hard on together in the Center for Mathematics of Information and Healthcare that we are directing together. So there we really work extremely closely with the clinicians and the medical researchers to make that happen, to really bring the mathematics to the forefront of medical research as well as towards clinical support tools. So the question is maybe to give some examples of how those models could help. So first of all, maybe something that is quite intuitively clear is, first of all, if you think about a patient and all the measurements that are being taken from a patient in the hospital, these are lots, right? So your blood is taken, that is sent to the lab, there are lots of laboratory tests being done, images are taken of different types. We saw positron emission tomography images, there are magnetic resonance tomography images, CT images, they all show different things, and so on and so forth. And so what is where mathematics or automated models in general can really help is to interpret, to integrate this patient data to really interpret how the patient feels and what the best treatment for a patient is from this integrated data. So really seeing all of this in a unified way. And this also gives us the capabilities of looking at this one patient who is coming in and comparing it with lots of other patients that this hospital or that that are contained in the data that we have used to build this mathematical model, that this model has seen before. The model can see patterns and make comparisons in this then high-dimensional space where this data collection of this patient lives. So it's really a way to make decisions, help clinicians to make decisions about patients in a more informed manner, taking them beyond what they have learned at the university and also beyond their own experience, but really building a context of lots more patients, many more patients, and also making the most of the data altogether. So this is one, and that can open up lots of things, right? So it can help clinicians to advise you on better treatments. It can help also to triage patients more quickly, so they can get to where they should be and the kind of treatment they should get more quickly. It can help to diagnose certain diseases earlier. For instance, to diagnose dementia earlier, to diagnose cancer earlier. The earlier you actually are aware of a disease, the more you can actually do to tackle it. Or, just think about even simpler diseases like celiac disease is super difficult to diagnose for pathologists, for instance, who are looking at biopsies. And mathematical models, AI, if you wish, really gives an opportunity to look at the data and make this connection to lots of other data points, other patients, other things that they've seen before, and really see maybe things in these biopsies that we can't see with our naked eye. And I think this is really the power where these models that we are developing can come in. Really as a collaborator for the clinicians and the medical researchers. Yeah. So, John, next question. So in the video, we discussed the challenges behind the explainability of AI and the reliability in particular, because we can't prove at the moment so much about deep learning, for instance. So does this create challenges to apply machine learning and mathematics to medical practice?
So I think that's a really good question. I think it's got a number of parts to it. I think it provides some challenges for mathematics in the sense that we need to do better. We need to understand what we really can prove, and we really need to go and really drive forward the work that is on explainable AI. I think with a lot of AI, machine learning, there are ways to do it in a way that is relatively black box, which makes it quite difficult to understand. There are then ways to try and take those black boxes and turn them into something that is more explainable. And really focusing a lot of the work from the mathematics community, from statisticians, and from people working in machine learning on how you turn things into something that is explainable will become, I think, one of the really driving research areas that we will see in the next few years. I think that's really important, but it does absolutely understand the flip side. And I think that we need to understand what it means when we have algorithms that we can't really explain. And I think from that point of view, what we need to work out, and this is again a very active area of statistical thinking, is what happens around bias. So this is wider than healthcare. This is about the use of algorithms, and how do we understand what the bias in these algorithms are, and can we quantify those algorithms, and can we in some ways, without even necessarily knowing how the algorithm works, can we design statistical tests, can we design statistical procedures that will give us an acceptable level of assurance that these things are not biased or don't behave in a way that we would find unacceptable. But I think there's also a set of interesting ethical questions which you think on the surface don't really have a lot to do with maths, but in actual fact probably do. And that's the set of questions that we're relatively happy to have doctors and others make a diagnosis, and then you go and see another doctor and you get a slightly different diagnosis. And so not all human decision-making is completely repeatable. So how do we quantify the levels of variability in human decision-making and compare that to the levels of differences in machine learning and other artificial intelligence? And can we come to a decision about what we believe is ethically acceptable? Now, many of those questions will be outside mathematics, but I think maths, statistics, machine learning can all add something into that conversation by really helping people understand what happens in a machine setting, what happens in human settings, and what is happening in comparison. And can we design methods that allow those comparisons to be really easily understood so that those who then have to make those ethical choices really have the best information available to them? So another question that we have is for you, Carola, is what currently unavailable data sets are holding back the potential applications of AI in healthcare settings? Are there privacy and ethical questions involved in those data sets?
Okay. Yeah, really good question again. So first of all, I think the main challenge for us is there are data sets kind of spread all over the world, the internet as well, different research groups in the world. The challenge is to bring those all together and to share data. So data is being shared in various ways. On the one extreme, let's say, there are medical imaging data sets that are online for medical image analysis people or computer vision people, for instance, to train their algorithms on. These are benchmarking data sets. So they have different kind of sharing rules than, for instance, data sets that exist in research groups in hospitals or universities, where they are shared with individual other research groups. So there is a lot of effort, both internationally and also in this country, for making this data sharing more of a standard thing. But it's a way to go. So the main challenge behind everything is really to share the data, and this is where we need to still invest some efforts. I mean, just to give an example, maybe of John and my work that we did recently related to COVID. There you could see, first of all, in March last year, that there was a lot of willingness to share data, where people were really just wanting to help. And so, things that weren't possible before all of a sudden were possible. But what you could also see is that some of the mechanisms we have with respect to ethics, for instance, are also sometimes too slow, in particular for an emergency situation such as a pandemic. Really large amounts of data that we developed our mathematical models on for, in this case, COVID-19 triaging in the hospital, were really coming in several months after the pandemic has started. So we had to work a lot with kind of put together anecdotal kind of data sets. And that, I think, is definitely a challenge, and we need to change something. But you could see that things are possible, definitely, in this emergency situation. And I mean, the NHS, in this case, has done a really wonderful job in creating a UK-wide database for COVID that we profited from. Yeah.
So, I mean, thank you all for your questions. I'm sorry we didn't get a chance to get through all of them. But I mean, hopefully you can see that we feel that maths has a really something to add to medicine, but medicine also has something to add to maths, and that we feel that there's an awful lot of questions that we can answer, and there's an awful lot of interesting work that we can still do. And thank you very much for your time.
Thank you so much. Thanks a lot for watching.